Hi guys, my name is Reis. I hope you're doing well and I welcome you to my new video. When we implement an Android app, most of the time we have an initial UI state at the screen. Then the user has some interaction or some other sources lead to some mutations of the state. The state itself is most of the time represented by, for example, a single object or any other sources. By mutating the state, the user triggers a recomposition of a composable and the state changes get represented on our actual screen. But what happens if the user, for example, rotates the device and triggers an orientation change? If the device has auto rotation on, the activity will get destroyed and recreated, which leads to state loss. That means that all the changes by the user that led to mutations of the state will be lost. In many cases, that might be okay, but there are also many cases in which we don't want that behavior. So the question arises, how can we actually retain our UI state across these configuration changes or process or activity recreations? That is exactly what we are going to look at today. First, let's start with an actual example at what happens if we just ignore these configuration changes. So let's dive into it. As an example, we have a cat here in a cat composable. We can quickly jump into the cat. It's just a data class with a name, age, and if it's fluffy. Then in this cat composable, we have some rows that show these properties and also a button which just increments the age of the cat. If we execute the app, we can see that we have the values here. Name fluffy. If it's fluffy, yes it is, and the age 1. So if we take a look, we have a delegate, ordinary remember, and a mutable state of this cat. So these are all the initial values. And if I click on the age button, you can see that the age increments. Let's quickly check out if our rotation is on. Yes, it is. Auto rotate is on. So now if I rotate the emulator, you can see that the state resets, and that is actually the problem because the state won't retain and we are back at age 1. So what do we need to do in order to retain the state? It's quite simple. We just don't use the remember, but remember savable function. Underlying this function uses the saved instance state to save our object in the bundle. That means, on the other hand, that we need to make sure that our objects implement parsable. Now that we replaced remember with remember savable, we might think, okay, and now we just need to start the app and everything will get stored in the saved instance state. But oh, as you can see, the app immediately crashed, and we see mutable state containing cat fluffy cannot be saved using the current savable state registry. The default implementation only supports types which can be stored inside the bundle. Please consider implementing a custom saver for this class and pass it as a state saver parameter to remember savable. In order to use this function, our cat needs to be of the type parsable. And how we do that is what we are going to look at in a second. Back at our cat, the only thing we need to do is to extend parsable. And now you can also already see a warning comes up that the cat is not abstract and doesn't implement members, describe contents, etc. So now we could implement these things by ourselves, but luckily there is a plugin from Kotlin that is called Kotlin Parcelize. This plugin provides us an annotation called parcelize. Make sure you use the Kotlin X parcelize import and not the Android import, which is deprecated. And now these functions automatically get generated. So now that we have our parsable cat, we start the app. And yes, it runs. Now I will reproduce the experiment from before. I increment the age, rotate the screen, configuration change happens, and we can see the age is still at 8. So now that we saw that if our cat object implements the possible interface, it can successfully get stored in the saved state registry. What if we have no access to the object itself? We cannot mutate it. What do we have to do then? In this case, we can make use of some helper functions. One is the map saver and the other function is the list saver. When we cannot let it implement the possible, we need to instruct by ourselves how these objects can be split up into atomic variables that are possible, or rather that can get passed into a bundle. We just need to implement the save function and the restore function. Another example is now our doc class, and we assume that we cannot implement the possible interface. The first example is now the map saver. For all these three variables, we define a key. One is for the name, one for the age, and one if it's cute. Now we have the first function, the save function. We get the respective dog and just map it to these keys. And we return here a map of string, which is the key, and any. On the other hand, when we receive the respective object from the saved instance state, we also want to restore the object. So we have our restoration map here and can just get our values back by accessing the keys and then recreating the instance of a dog. The same goes for the dog list saver, or rather the list saver function. Also takes a save and a restore function. In contradiction to the map saver, we use lists instead of maps. So we just pass in the variables, and the order here is relevant because in the restore function, we now have a list and just access all these objects via the indices. 0 for the age, 1 for the name, and 2 for the if it's cute. Now back at our example, regardless of the function that you use, it's really just a matter of taste. You just need to pass in the respective saver into the remember savable, pass it to the state saver, and you can use it just like before with the possible interface. Thanks for staying until here. I hope you had some takeaways. The code snippets can be found in the linked Medium article down in the description. Make sure to like the video, subscribe to my YouTube channel, activate the notification bell, and I hope to see you soon.